All right, so this is our last class of the semester. I'm sorry, we're done. Yeah, but we still have the final to look forward to. So that's going to be on Friday the 9th. We've talked about this before, that the exam's comprehensive. It's going to have both some concept and problem-solving questions. You can bring 3 pages of notes. Any questions about the final? I haven't written it yet, so I can't tell you what's on it. Otherwise, I totally would, but I just haven't written it yet, so.
You think you'll have the same soft tart you did for our last exam and give us a couple points?
The same what?
Remember you had a soft tart the last exam and you gave us 3 points?
Oh, no. Yeah, I've been cured of that.
Cured.
Yeah, that temporary insanity where I gave you some extra points, no. Yeah, I went straight into counseling, and so that's gone. Back to my normal hard heart. All right. So if you have any questions as you're preparing for it, I'll be in the office next week if you want to revisit any topics. Of course, the lectures are recorded. All of the solutions for homework assignments are posted on Blackboard. Unfortunately, I think I'm a couple of lectures behind on posting the notes. So I'll do that today. I'll get the PDF of the notes put onto Blackboard today for the last couple of sections. Let me take your pulse on one thing, though. I was thinking, somebody had previously asked, I think Josie, whether the software would be on the exam, and I said no. I was thinking that, let's say, what if there were 5 problem-solving questions that you had to solve, but I gave you 6 to choose from? And so you can pick which 5 you want to do, and one of them was a BioWin question. Would anybody be interested in seeing a BioWin question, or should I just go with the normal exam where I pick 5 questions and you do those 5 questions, you don't have the choice?
If we have the computers, does that mean that increases the chances of an Excel problem?
No, it means that you'd have to do the BioWin problem last, and that the BioWin would be the only thing that you'd use the computer for, so that you wouldn't have access to the computer during the rest of the exam.
Could you give us 7, pick 5, and one of them be an Excel, one of them be a BioWin?
No. No, the computer would only just be for BioWin. Yeah.
I messed up the class exam.
So raise your hand if you would want to see a BioWin question on the exam.
How complex would that
Well, I have a Mac, so
There doesn't seem to be a lot of enthusiasm, so we'll just skip it. All right, fine. That's okay. All right, so as from last time, we're going to be using BioWin today, and I've posted a starting file on Blackboard. So please go to Blackboard, and what you'll find is in the BioWin folder, this one that's called Friday Example. So download the Friday Example, and then once you've got it, you can open that file, I hope, assuming that that server's still running. Worked for me. This is the example that we were looking at last time. And we're going to change this to reflect a trickling filter, and then later to reflect an anaerobic sludge digester. So here's a handout that just describes the parameters of the inflowing wastewater and the trickling filter that we're going to add. Okay, so what we're going to do is we're going to modify the existing system by removing the aeration basin, and we're also, in doing that, we're going to remove this splitter, because the trickling filter, the way that they set it up in BioWin, is that there's not recirculation within the trickling filter, or if there is, it's an option that is embedded within the filter, and you don't have to add a separate external splitter to turn on recirculation within the trickling filter. So I'll give you a moment to download and open up that file and see. It seems like folks have got that going. Okay, so we want to put a trickling filter in instead of the aeration basin. So to do that, go into the Configure tab here and use the select, drag, edit tool so that you can click on the aeration basin. And by the way, I don't know if I specifically mentioned it last time, but when you hover the cursor over an item, down at the bottom, it gives you a summary of its characteristics. And some of them may be characteristics that we've annotated with these tags, but some of the characteristics we haven't annotated. For instance, you can see on this one, it's got pH down at the bottom. So if you had specified the pH of a flow that's coming in, you could monitor the pH because different treatment steps can affect the pH, whether you've got like a membrane bioreactor or if you're doing chemical addition. There's a variety of things that could adjust the pH. So when you hover over the sludge, for example, you'll notice it says the pH of the sludge is 6.79. You hover over the effluent, 6.79. So something along the way has adjusted the pH. And so what we're going to do is just select the aeration basin and then press the delete button, or I think you probably can right click and delete it that way. And it warns you. The interesting thing is there's no undo button, at least I don't think so. If you know, usually if you make a mistake, you can edit, undo. That doesn't exist in BioWin.
It's the top left arrow.
Where's that?
Underneath main. Like
Underneath.
I
configure.
don't think it undoes what you just did, it just removes things that you added.
Let's try.
You delete it and then press.
No, I deleted aeration.
All right,
basin.
so let's delete the aeration basin. If I accidentally did it, could I bring it back somehow? Oh, okay. There is an undo. Interesting that they don't put it under the edit because that's where it is in most software. But cool. All right. Glad to know that because I made some mistakes along the way and had to start over from scratch. So delete the aerator, delete the splitter, and let's put in a trickling filter. So the trickling filter icon is the one in here that looks like a packed tower. Trickling filter. So we'll just drop it approximately where that aeration basin was before. And you notice there's one thing coming in and one thing coming out. So we're going to take the flow off the bottom of the trickling filter and connect that to the clarifier. And then we have to connect the influent to the trickling filter. So let's put the pipes in that are needed to the trickling filter, and then the underflow from the trickling filter up to the influent of the clarifier. Now, since I deleted that splitter, because we're not recirculating sludge, we have to connect the underflow from the clarifier directly to the sludge. And then I'm going to just drag that pipe down so that it's not in the way of the annotation I had added before. So your system should look approximately like this. The handout I gave you specified the parameters for the trickling filter that we want to do. So, I mean, it's basically all the same inflow except for the flow rate we need to adjust. I think previously it was in the 30-something thousand cubic meters per day. Let's reduce the flow rate down to 10,000 cubic meters per day. So that is an adjustment that we have to make here in the influent. Double click on it. Edit data, and it was 34,560 before. Let's dial down this flow rate to 10,000 cubic meters per day. All right. Now, we had all of the pipes annotated, but when we deleted the pipes, those annotations were removed. So if we want that back again, we'll have to manually add it. So once again, I'm specifying below, tag the parameter, and what we want to have is the flow annotated. So add that to each of the pipes just so we can keep straight that I guess this system isn't quite as complicated as the flows since there's no recirculation, but it's still nice to see where things are going when there is a split. And we do split the flow going into that ideal clarifier. There's the underflow versus the overflow. All right, so we changed the flow to the influent. If we look at the parameters here in this new problem where we've got the trickling filter, we want the volume to be 900 cubic meters. So go into the trickling filter by double clicking on it, and it has some default assumed value. I think that's 2,000 cubic meters. Let's see what's going to happen if we have 900 cubic meters. And we'll leave the depth of the filter the same. It's interesting to see that they give you a variety of different media that you could choose. Rock is the default, but if you switch over to, for example, like structured plastic, then it has different specific area. So the default specific area it had is 50 square meters of surface area for a cubic meter of rock. We're going to tinker around with things and starting with rock, see what kind of performance we get. But then when we switch over to the plastic media and we have more surface area per unit volume, we may get better removal performance for the same volume of clarifier. So we'll stick with rock for now. We just changed the volume of the reactor, and that's all we're going to do. Notice here under the Operation tab, it says that let's assume that the water coming in has 4 milligrams per liter. It's going to calculate the concentration of dissolved oxygen in the middle of the trickling filter and then at the end of the trickling filter. Because if we send the water coming out of the trickling filter into the clarifier and the water's got no dissolved oxygen in it, then it's going to become anoxic or maybe even anaerobic in the clarifier, because the clarifier is very quiescent. We can't diffuse air bubbles in the clarifier or the sludge isn't going to settle. So remember, the clarifier has to be kind of like a stagnant pool of water where particles are settling downward, but there really isn't any air addition going on in the clarifier, except for maybe just a very limited amount of diffusion at the surface or at the top of the clarifier where the air-liquid interface is. But besides that, we need to be aware of how much dissolved oxygen is going into the clarifier, because there still is some BOD and there is a demand for oxygen that can occur in the clarifier. Okay, so we just changed the volume of the trickling filter to 900 cubic meters. We need to adjust the underflow from the clarifier because we've got 10,000 coming in. And I think previously we had said that the underflow of the clarifier was going to be 15,000 cubic meters per day coming off the bottom. And this problem statement says let's set the underflow of the clarifier at 500 cubic meters per day, because that's what's going directly to sludge rather than being recirculated. So change the underflow of the clarifier to 500 cubic meters per day. And now let's run the flow balance just so we can see what is the calculation of where the flow is going in certain places. Now you may have noticed that there was a pop-up warning there about calculating the hydraulic retention time, and we will do that before we have it calculate the biological calculations. It needs to know basically where is the water accumulating inside of this system? Like, where is their volume? Which elements in the network have volume that ought to be considered when calculating the hydraulic retention time? So we'll do that. But all I wanted to do so far with that previous step was just to show that there's, of the 10,000 that comes into the clarifier, 9,500 is overflow, 500 is going to sludge. Okay. So let's do that step of calculating the hydraulic retention time and the solids retention time. If you go here to the Calculators tab, let's do a new hydraulic retention time and select the elements for total volume. So in here, there's volume in the trickling filter and there's volume in the clarifier. And we want both of those, the clarifier and the trickling filter, to be accounted for when it's estimating how much time water spends inside of our system. Because it's going to do basically, flow rate and volume it will utilize to calculate time. Because time is volume divided by flow rate. Okay, so we've just specified the volume. Now here under flow elements, it's asking us what should it use as the Q when it calculates the hydraulic residence time. And it will get the Q from our influent. So the influent BOD stream is how we'll define the flow rate in this system. Okay, so we've defined the hydraulic retention time. Let's also define the solids retention time. Solids retention time here is going to be pretty simple because there's not recirculation. When we were doing the aerated system, we were recirculating sludge solids, and so the hydraulic and the solids retention time are different and depend on the ratio of the split. That's not the case here, but we'll calculate a new solids retention time anyhow. Select the elements for total mass. This is similar to the previous step. It just wants to know, like, where is their biologically active mass. And so it's in the clarifier and it's in the trickling filter that microorganisms are alive. It's where they exist. And then where is that being wasted? We're going to select the sludge stream for the place where the sludge solids are discharged from the system. So, okay. So we've calculated a new solids and hydraulic retention time. Now, with this 900 cubic meter reactor, and we're leaving the clarifier volume the same, 20,000 cubic meters. The only thing we needed to change on the clarifier was the underflow. We're trying to get 15 milligrams per liter of BOD, and we want the water coming out of the trickling filter to be at least 1 milligram per liter of dissolved oxygen to make sure that inside of the clarifier things don't go anoxic. So let's calculate. So under the Simulate tab, Steady Flow Balance, and since we're starting from scratch basically, like we haven't already done a previous calculation run with the trickling filter, we'll start with the seed file rather than with the current values. So starting with the seed, begin the calculations, and fingers crossed it can find a solution here. It did within 3 iterations. Okay, but we've got alarms. Sometimes it just says solution found, but here it says solution found with alarms. So it's detecting that there's some sort of an issue, and we get this pop-up thing here saying the specified dissolved oxygen set point cannot be achieved. So something's up with dissolved oxygen. Let's hover over the trickling filter and see what we can learn. If you see the cursor over the trickling filter, it's saying that the dissolved oxygen at the filter top is 4 milligrams per liter, but then 1.31 milligrams per liter in the middle of the trickling filter, and by the time the water gets down at the bottom, there's only 0.44 milligrams per liter of dissolved oxygen. So that's too low. The water going into the clarifier has so little dissolved oxygen that it's going to, all the rest of it will be consumed in the clarifier, and we'd have a layer of anoxic sludge at the bottom of the clarifier. So we need to make changes. Either we need to increase the rate of the blowers that are providing oxygen into the trickling filter, or we need to increase the size of the trickling filter. And I think that we ought to go with the latter, because if you check the BOD of the effluent, it's also not meeting our required standard of 15 milligrams per liter. So this solution is a fail for 2 reasons. We haven't got the BOD that we need, and we also haven't got the dissolved oxygen that we need. Okay, so 900 is too small. Let's see what we could do with 4,000 cubic meters for the trickling filter. Okay, so instead of 900 cubic meters, let's try 4,000 cubic meters. Okay, and then let's run the simulation again. Steady state balance. Now this time I'm going to have it start from the current values and calculate. Maybe it'll iterate more quickly. No, it's taking even more. Hopefully it finds a solution here. If not, then I'll have it start from the seed rather than from the current values. All we've done is make the trickling filter bigger, so I'm a little surprised it's taking so long to calculate, but at least it says now with solution found, we're not getting that alarm. We had the dissolved oxygen alarm when the filter was too small. Because basically what we were doing, when the filter's too small, is we're loading a lot of BOD over too little media. And so the ratio of food to oxygen is off when you've got a really small filter. Here, by having a larger filter, we're kind of spreading out and have a lower loading rate, mass loading rate of BOD per surface area. So solution found, let's take a look by hovering over the trickling filter. We still have that 4 milligrams per liter of the oxygen coming in, and we're just barely above 1 milligram per liter in the effluent. So we might be able to reduce the volume of that reactor down a little bit from 4,000 to maybe like 3,950, I don't know. But we won't play around with that, because I think what I'm more interested to find, okay, so we've answered, by the way, question 1 here. Evaluate the proposed volume. The proposed volume, somebody had suggested, I guess, what if we went with a trickling filter of 900 cubic meters? And so our analysis says, that's not suitable. It doesn't allow us to achieve the required BOD removal. It also, it's not acceptable from the standpoint of dissolved oxygen. Okay, so that proposal's no good. So what is required? We'd say 4,000 for rock media. I'm curious to know what would happen if we switched in a different media besides rock. That's actually not something that I've played around with yet. So let's try that right now. What if we switch from rock media to structured plastic cross flow? So now we've got different specific area because there's more surface area in that structured plastic. I'm not sure. It looks like some of the terms down below here are also being adjusted. Hydraulic rate, loading switch. We're still saying that we'd like it to start with incoming dissolved oxygen at 4 milligrams per liter. Now, how would you actually achieve that if that wasn't the case of your flow that's coming in? You could have a pre-aeration step, a miniature aeration basin that doesn't have any recirculation of sludge, just to get it up to 4 milligrams per liter before it goes to the trickling filter. So we're just saying the flow coming in has 4 milligrams per liter of dissolved oxygen. So we're sticking with the 4,000 cubic meter. The thing I want to know is how does the BOD change? Because, by the way, what was the BOD when it was rock? I don't know if it's already changed that. So with rock, simulation of 4,000, which is what we had to do to get the dissolved oxygen that's needed. So the BOD is 10. Okay, so I'm going to write this on the board just to keep track of it. Rock, media, the DO is 1.0, what was it? 1.03 milligrams per liter. And then the effluent BOD was 10.04 milligrams per liter. All right, so let's just see what effect we get sticking with the same volume but switching over to structured plastic. I don't know if it'll have any effect, but we've made the change, and let's run the simulation. With alarms. All right. Dissolved oxygen. We've got a dissolved oxygen issue. The BOD came down, but the dissolved oxygen is worse. I suppose because in the case of the structured plastic, when you've got a larger specific surface area, it would follow that you need more air being pumped into the trickling filter because it's kind of like you've got smaller pore sizes to get that increased surface area. So that's interesting. All right, so let's put it back to the rock. And now I'm going to pause for a moment because I'd like you to try and investigate, if you have 15 degrees Celsius water, then how big should the trickling filter be with rock media? So let me put it, I've switched it to rock. Let me run the model again, run the simulation. It had assumed 20 degrees Celsius water by default, and I'll show you where that is that you can override it. You can do like a local override that only applies to the trickling filter itself, rather than having to change like that all the water in the whole system is a certain temperature. Hopefully it'll converge any moment now. I might just go back to the seed if the current values are taking so long to converge.
It quits at 60.
16?
60.
60? All right. Yeah, odd. All right, I'll go back to the seed because these values are nothing that it hasn't seen before. Terminate simulation. All right. Yeah, 4,000 and we're at rock. So it found the solution to this before. I'll just steady state with the seed rather than the current values. All right, start. Solution found, finally. Boy, the suspense was killing me. All right, so we're back to our normal 10 milligrams per liter is the BOD coming out. Okay, so what I want you to do is find out what if we make the water colder. What if, so double click on the filter and you can find out that you can specify a local temperature on the operation tab. Right now it's assuming that it's 20 degrees Celsius. But what if it was 15 Celsius? I would presume that these microorganisms aren't going to be as efficient as they were at 20 Celsius. So how big does the trickling filter have to be to achieve 15 milligrams per liter if the water is colder? Okay, so I'm not going to narrate through. I'll just pause from my talking for a minute so you can work on that. It's kind of interesting that reducing the temperature didn't actually affect the performance all that much. Taking it from 20 to 15, I got that the effluent BOD only goes from 10 milligrams per liter to 11.5. Did anybody else get similar values?
Yes.
11.5? So it didn't have much impact, although if you notice the dissolved oxygen in the trickling filter goes down a little bit. So we have a little bit of a slide, because it was at 1.03 milligrams per liter. Then it gets to 0.96 milligrams per liter for the dissolved oxygen. So the temperature sensitivity isn't so bad at 15 Celsius. I wonder if that would be the case if we continued to make it even cooler. Like if we took it down to 10 Celsius. I would have to guess that the reaction slows down as we continue to get colder. That the effluent performance is worse if the microorganisms are chilled and not consuming as much substrate. Yeah. So when we took it to 10 degrees Celsius is when we see maybe a more noticeable reduction in the removal efficiency, because now the effluent is up to 15.5 milligrams per liter. So directionally, things are happening as we'd expect. As the trickling filter gets colder, so does the removal efficiency decline. With the 10 minutes that are left, what I want us to do is take a look at adding a digester, an anaerobic sludge digester. So I'm going to put the trickling filter back to its original temperature. So I'm going to put it back to 20 degrees Celsius. I'll just turn off the local temperature. And we want to digest this sludge. So we have to delete the effluent that's there. I don't know if we can drop a sludge digester in an existing stream and it will split the stream. I don't know. I haven't tried that, but let's try it now. So here's an anaerobic sludge digester. It looks like a cylinder with little flexible gas collecting roof on top. It's next to the mixer. So digester anaerobic. Let's try dropping it. I don't think it split that pipe. So I'm going to have to just select and delete that existing pipe and then connect the dots. All right, so connect the bottom of the clarifier to the inflow of the digester, and then the outflow of the digester we're connecting to the sludge. And then we can move the location of things a little bit to make sure that the diagram makes sense to us. All right, so the water goes to the effluent, the sludge goes to the digester. Now let's double click on the digester and bring up its characteristics. So look at the sludge before, we haven't executed the model again. Before we add the digester, where are things at with the volatile suspended solids? So volatile suspended solids and the BOD, we want to see if we can knock those down a little bit with the digester. So BOD is 1771 in the sludge before the digester, and then the VSS, volatile suspended solids, are 2445. Okay. So the problem statement says that we want to have the sludge at 35 degrees Celsius for 30 days. So our sludge rate is 500 cubic meters per day. You remember that is defined in the underflow of the clarifier. So our underflow rate was 500 cubic meters per day. So we want 30 days of storage time. So 500 times 30, that's the volume that we need for this digester. Let me just do that quickly. That's 530, 15,000 cubic meters. So double click on the digester. Let's put in a volume of 15,000 cubic meters, because that will give us 30 days of storage. And we'll just leave the headspace pressure and volume the same. We had said that we want it to be at 35 Celsius, which happens to be the default temperature assumption under here in the Operation tab. We could, if we wanted, specify the power consumption and so on. I don't think there's anything necessarily that we need to tag on the digester, because it's here the sludge characteristics that we're going to be able to see the impact of running that digester. Okay, so let's run the simulation again. So simulate steady state flow balance. We may get a new warning because we've added a new flow element about the hydraulic or solids retention time, but that's all right. I don't think we need to change anything there. Let's just see, how did the BOD and the VSS get affected by adding that digestion step, 30 days at 35 Celsius? What's happening to our sludge? Solution found. All right, no warning message. Happy to see that. Wow, it had a really nice effect on both. The BOD went from 1,700 down to 200, which, I mean, you could feel good about land applying sludge if the BOD is down in that range. Volatile suspended solids went from 2,400 down to 700. So sludge digestion works, at least according to BioWin. That was at 35 Celsius. Now, what if we warmed things up a little bit more? What if we warmed it from 35 Celsius to 40? The question is, could we make the digester smaller and still achieve this same result? So right now the result after digestion, sludge before, the after, the BOD is 204 and the VSS is 785. We warm things up in the digester to 40 Celsius. Let's run the simulation and see what kind of effect that has. Should be even lower. And since it'll be lower, I think that could enable us to reduce the size of the digester, which would reduce the retention time. But remember that in anaerobic digestion, what you're trying to accumulate is a certain amount of degree days. So if it's warmer, you don't have to store it as long. It's just so perplexing. It takes so long to finish the simulation. There it is. All right. So 186 and 771. It didn't change the VSS much to warm things up, but it did adjust the BOD a little. Not a lot. So we're not going to be able to reduce the size of this digester too much. We were at 15,000 before. I think if we go to 14,000, probably we'll be worse off than we were before. But of course, you know that design is this alternating process of adjustment, investigate the effect, and iterate. So that iterative process of making a change, tinkering around, finding out if you make the digester smaller, you could save money, but then how does that affect performance? So I just took it from 15,000 cubic meters to 14,000 cubic meters. And let's see what happens with the BOD, because it's at 186 and we want to keep it around 204 by making the reactor smaller.
Hers got really close at 12,500.
12,500?
Yeah.
Yeah, because at I did 14 and it's not yet too high, so maybe we could go quite a bit smaller, 12,500. Okay, it's 12:48. We are out of time. The semester is finished. We'll meet a week from today for the final exam. I'm going to have two things for you that day. I'm going to have the final exam, and I'm also going to have a very short survey that you have to fill out for how well you feel like we accomplished the course learning outcomes. So we'll do that. That'll take like 2 minutes at the beginning of the final.
Do we have a chance to win a $10 Amazon gift card? Filling out a survey?
All right. Thanks.